On section 3.5, we're going to cover rational functions and their graphs. Now, remember what a rational function looks like. It is a function that has the variable x on the denominator. So, basically, this is the general definition. Rational functions are quotients of polynomials, mainly f of x equals a polynomial divided by another polynomial. That is what makes a rational function. Keep in mind that on a rational function, we have some values. The domain of rational functions is not negative infinity to positive infinity, because anything that causes the denominator to be 0 is going to make it undefined. It's going to make the function undefined, meaning that the value, for whatever value makes the denominator 0, will not exist on the graph of that function. So, the function, any rational function, is defined for any value, with the exception for anything that causes the denominator to be equals to 0. Okay? So once again, the domain of a rational function is a set of all real numbers except the x values that make the denominator 0. So let's go ahead and start with this question. Very simple. We're going to find the domain of this function. So remember that the domain of any rational function is going to include any value with the exception of whatever causes the denominator to be 0. So first thing we need to do, we need to find whatever value or values that make this denominator equal to 0. So if I solve for x, then we're going to get x equals negative 12. So negative 12 makes the denominator 0. So what does it mean? That negative 12 is the only value that must be excluded from the domain. That will not be in the graph of this function. So we can write the domain in two different ways. The set notation would be the set of all x such that x is not equal to negative 12. That is one way. Or in interval notation, how would you write it? You're going to say that the domain is anything from negative infinity and then it stops at negative 12, or anything after negative 12 all the way to positive infinity. So this is a domain either in set notation or in interval notation. Now, the next thing is this. We're going to look at the definition of a vertical asymptote. Now, any value at which any value that causes the denominator to be 0, this is one of the things that can happen. Anytime that the denominator is 0, that means that the function is not going to include that value in its graph, because there is no y value if the denominator is 0. The value is undefined. So what happens is, this is one of the things that can happen. At this value of a that makes the denominator 0, there's going to be a vertical asymptote, meaning that once the graph gets close to this value, the graph is going to slant vertically upward towards that line, or vertically downward towards that line. But it will keep getting closer and closer to that value, but it will never get to that value since it makes the denominator 0. Okay, so that's how the vertical asymptote will actually look like. Now the question is, how do we find the vertical asymptotes? Basically the same way we find the domain. However, for a vertical asymptote to exist, the first thing you need to do is that you need to make sure that the rational function have no common factors, meaning that it is reduced as much as possible. Okay. Now, if a factor, if the rational function is already in lowest terms, meaning that it's already reduced, then any value that causes the denominator to be 0, it is going to be a vertical asymptote of the function. Okay. Now, what happens if we can simplify any of the factors? Then if that happens, then whatever factors can be reduced, it is not a vertical asymptote, because it is what we call it a removable discontinuity. If I simplify any of the factors on the fraction, then it is called a removable discontinuity, which in other terms is called a hole in the function. I'm going to show you basically what the hole means and how it looks like graphically. So let's start with this question here. Well, I think this one's better because it's not factored. So we're going to find the vertical asymptotes, if any, and the values of x corresponding to holes, if any, of the graph of the rational function. So first thing that we can do in here is that we can simplify this, so we can factor it. So the x minus 1 cannot be factored, but the denominator, we can factor it out. So that's a trinomial, so for this one we need to multiply a times c, which is 1 times 4. And that is going to give us a 4. So then we need to find two numbers that multiply to 4, and at the same time they add up to -5. That would be 4 and 1, but both of them must be negative. So it would be -4 and -1. Then we're going to put x on both. Now, let me ask you this. Now, if we find the values that make the denominator 0, so what value makes this denominator 0? So if I set it equal to 0, that gives me x is equal to 4. Now, what value makes this denominator right here 0? Then if I set it equal to 0, we can find it, and that would be x equals to +1. So these are the two values that make the denominator 0. But just because they make the denominator 0, that means that automatically they are vertical asymptotes. Now, first thing that we need to do, so well, we find those values, but then we need to check if we can reduce this fraction. As you can see, we have an x minus 1 and x minus 1 on the numerator and denominator, so that means that we can simplify the x minus 1. Anytime that we simplify a factor, that's called a removable discontinuity. Removable discontinuity is also called a hole in the function. So that means at x equals to 1, there's going to be a hole. I'll show you how that looks like. And this factor that we have left, which is x minus 4, that one is going to be my vertical asymptote. Okay. So now let me show you basically how the hole and the vertical asymptote looks like if we graph this function. So you see that on my new function, once I simplify it, we are left with 1 over x minus 4, right? Because there's nothing left on the numerator, that means we have a 1. Now let's look at the calculator, and let's do that here and see, so I can show you how the whole looks like. Okay, so we got this. So we're going to go to the y equals, and we're going to put the original function in. So make sure you put the numerator and denominator in parentheses anytime you graph a rational function. So x minus 1 divided by, and then another parentheses, and we have x squared minus 5x plus 4. Then we're going to graph it. And I'm just going to paste the graph of this function right over here so you can see. So based on the graph tells us the following. Now, the vertical asymptote means that the graph is going to slant vertically once it gets close to x equals 4, meaning that it's going to get very close to 4, but it will never get to this value 4. That's the line that you see there. And you see that once the graph gets close to that 4, it's going downward, and it's just getting closer and closer and closer to it, but it never gets to 4. Also from this other side, the graph keeps getting closer and closer and closer to it from the right, but it never gets to 4. That's what the vertical asymptote does. So once the graph gets close to that value that causes the denominator 0, which is my vertical asymptote, the graph is going to deviate vertically downward and upward from either side. Or maybe sometimes we're going to see that both of them could go the same direction. That's things that we're going to analyze later. Okay. Now, you see the whole x equals 1. At x equals to 1, you see that the graph it looks like it is passing through x equals to 1, but in reality it isn't. It is passing through 1, but 1 is not included. A hole is basically the same thing as an open circle, just like we talked about it in the piecewise function. That's what a hole basically represents. An open circle, it means that the graph passes through that number, but that number is not included in the graph of this function. And you can see that if you go to the table in your calculator, you can actually see the hole. So you might think that it contains the number 1, but if you go to the table by pressing second and graph, you see that at x equals to 1, there is an error, meaning that the graph does not contain that value of 1. but it doesn't look to be a vertical asymptote. So what does it mean? That it is a hole. This is what the hole looks like. Okay. Now, let's do another question on vertical asymptotes. So now we're going to do the same thing here. Find the vertical asymptotes, if any, and the values of x corresponding to holes, if any, of the graph of this rational function. Now, the numerator cannot be factored, so the numerator is going to stay as is, right? And then x squared plus 20, the denominator also cannot be factored, because that looks like differences of squares, but it is not a minus. So remember, anytime, this is something I mentioned in P5, anytime I have a polynomial in the form a squared plus b squared, that's automatically prime. We cannot factor that. So all we're going to do then, so this cannot be reduced, so it's already simplified. So in order for me to find the vertical asymptotes, we're going to do this. We're going to set the denominator equals to 0. By the way, the fact that we were not able to simplify anything from this function, it tells us one thing, that there is no holes in the function. Okay, this is one thing that we can already say anytime there's nothing that can be simplified, because there's no removable discontinuity. Removable discontinuity, it's a factor that can be reduced, and there's none. So now to find the vertical asymptotes, we're going to find the values that make the denominator 0. So in order for us to find that, let's solve for x. So I can move the 20 over to the other side. So that gives me x squared equals to negative 20. And then to get rid of the square, just like we covered in section 1.5, we need to get the square root on both sides, and that's a plus or a minus. But what's the problem here? What is the square root of negative 20? This is a non-real solution, or imaginary solution. Okay. What does it mean by the asymptotes being non-real? It means that there is no vertical asymptotes. So this function right here does not have any vertical asymptotes, and it does not have any holes, not at all. And we can actually see that from the graph. If you graph it, you would see that there is no vertical lines where the graph deviates, and there will not be any value where the graph gives you an error on the table. So this function is defined for all the values of x. There's nothing that will make the fraction undefined. Now, the next thing is, now we're going to look at the definition of horizontal asymptote. Now, horizontal asymptote, just like the vertical asymptote, it is a horizontal line that the graph, from either side, it keeps getting close to, but it never reaches. So basically, it lands horizontally either to the left or to the right once the graph of a function, of the rational function, gets close to that number. Horizontally, of course. Now, the thing is, how do we find the horizontal asymptote? There are 3 rules that you need to keep in mind. For locating horizontal asymptotes, all we need to look at is we need to look at the degrees of the numerator and the denominator. That's basically all what I need. Now, these are the rules. What does it mean by the degrees? The highest powers. So the rule says that if the degree of the numerator it is smaller than the degree of the denominator, that's rule number 1. Then that means that there will be a horizontal asymptote at the line y equals to 0. Y equals to 0 is the same thing as the x-axis. That would be the horizontal asymptote if the degree of the numerator is smaller than the degree of the denominator. Second rule states that if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote can be found by dividing the leading coefficients. The leading coefficients is the number in front of those x's. So when the degrees are the same, you just divide the leading coefficients, a to a sub n over b sub m, that you see there in the front, and that will be your horizontal asymptote. Y equals to the division of the coefficients. And last but not least, if the degree of the numerator is bigger than the degree of the denominator, that's rule number 3, then there is no horizontal asymptote on the graph. That means that the range will be from negative infinity to positive infinity. There will be no stops in the graph. Now, let's go ahead and take a look at a couple of horizontal asymptotes. Question here says, find the horizontal asymptote, if any, of the graph of the rational function. Now, to find the horizontal asymptote, we have to look at the degrees. So if you notice right here, this is this degree, this n, this is my degree of 1, and this is m, this is a degree of 2. Okay, so what do we see here? Rule number 1, it tells me that n is less than m. The degree of the numerator is less than the degree of the denominator, and by definition, what is the horizontal asymptote if the degree of the numerator is less? Y equals to 0. So that's simple. Just make sure you learn the definitions. Now, the next one. Now we see that now the degree of the numerator n is 2 and the degree of the denominator m is 2. So this is rule number 2. N is equal to m. When the degree of the numerator is equal to the degree of the denominator, how do we find the horizontal asymptote? By dividing the leading coefficients. So that's what we have to do. Divide the leading coefficients. Which in this case it would be y equals to 28 divided by 7, and that will be y equals to 4. This is the horizontal asymptote in this case. Last but not least, look, you see right here that the degree of the numerator, which is n, is bigger than the degree of the denominator, which is m. That's rule number 3. When n is greater than m, then by definition there is no horizontal asymptote. And that concludes this part on horizontal asymptotes. Now, the next thing we're going to do is we're going to look at some special graphs of functions, the two general functions, and we're going to use transformations to sketch the graphs. Now, first of all, let's go through the definitions of what we call the basic common functions. We're going to add these two functions to the family of common functions that I went over with you back in sections 2.1, 2.5, and 2.6. So we discussed those family of functions. We're going to go back to them, and we're going to add these two. Now the first one is 1 over x. F of x equals 1 over x. So if I create a table of values, well, before I create the table, there's some things that I want to mention to you. Now, if you look at this function, the vertical asymptotes can be found by finding the values that make the denominator 0, which in this case is x equals 0. That's why you see right here that there is a vertical asymptote right here on the y-axis, which is the line x equals 0. Now, to find the horizontal asymptotes, you look at the degrees. Since I'm going to put something right here. Since the numerator does not have an x, that means that it is x to the 0 power automatically, and the denominator is x to the first. So you see that the numerator, which is n, is less than the denominator, which is m. Rule number 1, which tells you that if the degree of the numerator is less than the denominator, then the horizontal asymptote is y equals to 0, and which is the x-axis. That's what we see right here on the black line. Okay, those are the two asymptotes, either for 1 over x or this one, which is 1 over x squared. 1 over x squared is going to be the exact same deal. Now, let's look at the graphs. Now, if we create a table of values for each one, now let me show you what's going to happen. I'm going to generate a little table for the first function right here, so you can see the values. This is 1 over x. So if x is negative 2, if x is negative 1, if x is 0, if x is 1, and if x is 2. There's also a couple of decimals there. So if I substitute a negative 2, 1 divided by negative 2 is negative 0.5. And that's what you see here. When x is negative 2, y is negative 0.5. When x is negative 1, so you're going to have 1 divided by negative 1, it's going to give me a negative 1. So you see, negative 1, that's another point. And then when x is equal to 0, 1 divided by 0, it cannot divide by 0, so it's undefined. That's where we see the vertical asymptote right here on my undefined solution. Then when x is equal to 1, you're going to get 1 over 1, which is 1. So it would be 1, 1. That's what you see here. And when x is equal to 2, it's 1 over 2, which is 0.5. So it's going to be 2 and 0.5. Okay. And just remember what I told you, when the graph gets close to the asymptotes, it's going to slant vertically and horizontally towards the asymptotes, in the direction of the asymptotes. So right here, the graph slants vertically upward right here towards this asymptote, and slants horizontally to the right, towards the horizontal asymptote. Same thing happens on the other side. If I connect these 2 points, when the graph gets close to the vertical asymptote, it's going to slant vertically downward right here, and it's going to slant horizontally to the left. So that's the graph of 1 over x. Now, the only difference for 1 over x squared, if you do the table for this one, let me show you what you're going to get, so you can see. So let's create a table with the values of, again, -2, -1, 0, 1, and 2. So if I substitute those values, 1 divided by -2 squared is 1 divided by 4, which is 0.25. So at -2, you see that the value of y is 0.25, right there. When x is -1, so it would be 1 over -1 squared, which is 1 over +1, which is 1. So -1, +1, that's what we see here. Then you see that now if we connect these points, the graph keeps on going up right here. So when the graph gets close to the vertical asymptote, it's going to slant vertically upward. And when the graph gets close to the horizontal asymptote down here, it's going to slant horizontally to the left. Now, on the other side, when I substitute a 0, 1 divided by 0 squared is 1 divided by 0, which is undefined. So at x equals 0, the value is undefined, meaning that there's a vertical asymptote at x equals 0. Now, at x equals 1, so it's going to be 1 over 1 squared, which is 1 over 1, that is 1. So 1, 1, this is the point that you see right here. The next one, when x is 2, 1 over 2 squared, it's going to be 1 over 4, and 1 over 4 is 0.25. So when x is equal to 2, y is 0.25. So once again, you see that when the graph gets close to the horizontal asymptote, it slants horizontally to the right, and when it gets close to the vertical asymptote, it slants vertically upward. Okay. So we're going to use those 2 tables that we have right here, and we're going to sketch transformations of these functions. Let's start with this one. Use transformations of f of x equals 1 over x to graph g of x equals 1 over x minus 5 plus 7. Use transformations. So we're going to begin with f of x equals 1 over x. So that's as usual. I'm going to graph that on the left side. And for that, I'm going to create a table of values for that. Okay. Alright, so for 1 over x, let's go ahead and create a table, and we're going to pick the usual values, -2, -1, 0, 1, and +2. So when x is -2, we already got the value on the previous slide. 1 divided by -2 is -0.5. I'm still going to get them again. So get you used to the finding values of rational functions now. So 1 divided by -1, it's going to give me -1. 1 divided by 0, that one is undefined. Remember that this is where my vertical asymptote is going to be. Then 1 divided by 1 is going to give me a 1, and 1 divided by 2 is going to be 0.5. So for the function f of x equals 1 divided by x, we get the points -2, 0.5, -1, 1, then 0, that one is undefined, so we're not gonna use that. So that's a vertical asymptote. So I'm just gonna point out to this one at x equals 0, so you remember there is going to be a vertical asymptote. Okay. Then the next one is 1, 1, and the last one is 2, 0.5. So let's go ahead and graph those things here. -2 and 0.5, so that is going to be right here. The next one is -1, 1, it's going to be here. So, and then there's a vertical asymptote at x equals 0. So that means that the graph is going to slant vertically upward once it gets close to this x equals to 0 line. That's why you see that it's happening on this graph. The graph once it gets close to this line, it's going to slant vertically upward. And it's going to keep getting closer and closer and closer to the asymptote, but it will never get to the asymptote. Now, on the other side, remember that if you look at the degree of the numerator and the denominator, we said that the degree of the numerator, since there is no x, it is x to the 0 power. And this one on the bottom is x to the first power. So that means that the degree of the numerator is less than the degree of the denominator. When that happens, there is also a horizontal asymptote right here at y equals 0. Okay, so y equals 0 would be my horizontal asymptote right here, and x equals 0 would be my vertical asymptote right here. Okay, so what does that mean? That when the graph gets close to the horizontal asymptote on this side, it's going to slant horizontally, and it's going to keep getting closer and closer and closer and closer to the asymptote, but it will never reach this value of 0. That's how the graph of that 1 over x will look like from that side. Now let's finish the points. Now the next one you see, it's a 1, 1. So 1, 1 is going to be right here. And the next one is 2, 0.5. 2, 0.5 is right here. Same thing is going to happen from this side. If you connect these points, you see that the graph is going downward to the right. So once the graph keeps approaching this horizontal asymptote, it's going to keep getting closer and closer and closer to it. It's slanting horizontally to the right, but it will never touch this asymptote. Likewise, as the graph gets close to this vertical asymptote, the graph is going to keep getting closer, closer, and closer to it, and it's going to slant vertically upward. Oh, there's only one little thing that I noticed that I didn't transfer. This was supposed to be negative, and this was supposed to be negative. I'm just going to fix that right now. So this is a negative 0.5, this is a negative 1. So that means that this curve that we have on this side should be going on the bottom, should be on the bottom. So let's go ahead and change this one right here. Okay, there it is. So you see that it was supposed to be a negative 2, negative 0.5, which is down here. And the next one is negative 1 and negative 1 right here. So it is the exact same thing, but it is slanting downward right here towards this asymptote, getting closer to it. And it is slanting horizontally to the left, getting closer and closer and closer to that asymptote. So that's the function that we talked about on the previous slide, which is 1 over x. Now we're going to use transformations to sketch the graph of g of x. Now let's remember from the transformations section, what is it that this number right here, the -5, is going to do to the function? That one is going to shift it to the right 5 units. Remember that the horizontal shift is always going to be first. So the first thing I'm going to do is the x minus 5. Meaning that it's going to shift to the right 5 units, and that means that all of the x's will be added 5. That's what we have to do. So add a 5. This is also an x, you see? So we're going to add 5 to that x also. So if I add 5 to all the x's, then this is going to give us the following. The point 3, negative 0.5. Then 4, negative 1. And then what about my vertical asymptote? It is going to become x equals 5. That's what the new asymptote is going to be, right? So that one is still my vertical asymptote, but now it's at x equals 5. The next one is going to be 6, 1, and the next one is 7, 0.5. So I'm not going to sketch it right now, so I'm just going to do the whole thing, okay? Remember that I don't need to sketch it by pieces. So I'm going to go now to the last transformation so we can create g of x. So we already did 1 over x minus 5. The last thing is we need to do the plus 7. That plus 7 means that the graph is going to be shifted up 7 units. So that means that if it shifts up 7 units, that means that all of the y's will be added 7. So all of the y's will be added 7. So that vertical asymptote doesn't change, right? Because that's not a y. So then we're going to get 3, 6.5. Then we're going to have 4, 6. Then we're going to have 6, 8. and then we're going to have 7 comma and then 7.5. So let's graph those points and see what it looks like. This is what my final g of x is going to be. So when x is, well, we know that the vertical asymptote is going to be located at x equals 5. That's for a fact. So let's draw the vertical asymptote here. Then my points, we are going to have 3 comma 6.5. 6.5 is going to be located right here. Then 4 comma 6. So 4 comma 6. Right? And that's what we see. And now one more thing. Oh, well, let me graph them all first. So 6 comma 8. 6 comma 8 right here. And 7 comma 7.5, which is right here. Now let's look at one more thing, the horizontal asymptote. Okay. Now we already know that when the graph gets close to this asymptote, because of the direction that is coming, it's going to slant vertically in this direction here, and this one is going downward, so you see it's going to slant vertically in this direction right here, getting closer and closer and closer to that asymptote. Now the thing is the horizontal asymptote. Since the graph was shifted up 7 units, remember that we said that all of the y's needed to be added 7. And that also applies to the horizontal asymptote. That's a y. So if I add 7 to it, meaning that this one is also moved 7 units up. So my new asymptote has to be right here at the line y equals to 7. So we're going to draw a horizontal asymptote at y equals 7, and that's where my asymptote is going to be. So what does it mean? That as the graph gets close to this asymptote from both sides, it is going to slant horizontally to the right on this direction, and it's going to slant horizontally to the left, getting closer and closer to this asymptote in this direction, and it keeps on going. And that will be the graph of g of x using transformations. So let's go ahead and do one more transformation. So we're going to use transformations of f of x equals 1 over x squared to graph g of x equals 1 over x minus 6 squared plus 5. So we're going to start with f of x, which is 1 over x squared. Okay, so let's create a table for this. So let's put the values. So we have a -2, -1, 0, 1, and +2. So if I substitute those x's, 1 divided by x, which is -2 squared, that's going to be 1 divided by 4, which is 0.25. Now, 1 divided by -1 squared, that is going to be 1 over 1, which is going to be a 1. Then 1 divided by 0 squared, that's 1 divided by 0, which is, we said, is undefined. So this is where my vertical asymptote is going to be located, right? Then this is 1 divided by 1 squared, which is going to be 1 divided by 1, and that is 1. 1 divided by 2 squared, that is going to be 1 over 4, which is going to be 0.25. So for the function f of x equals 1 over x squared, these are my points. -2, comma 0.25. -1, comma 1. Then there is a vertical asymptote at x equals to 0. Then 1, comma 1. And 2, comma 0.25. Let's graph f of x. So we know that there will be a vertical asymptote at the line x equals to 0. So that's what we're going to see. So right here in the middle, we're going to draw our vertical asymptote at x equals 0. And likewise, before I graph the rest of it, remember that since this graph, the degree of the numerator is still smaller than the degree of the denominator, there is also a horizontal asymptote at the line y equals to 0. Okay, those are my asymptotes. So I'm going to put the equations. This is my asymptote y equals to 0, and this is my asymptote x equals to 0. Now let's go ahead and sketch the points. We have that when x is equal to -2, y is equal to 0.25, which is somewhere around this area here. When x is equal to -1, y is equal to 1, which is somewhere over here. And then when you connect them, the graph is increasing right here, meaning that once it gets close to the asymptote, it's going to keep getting closer and closer and closer to it, but it's just going to slant vertically upward, but it will never touch the asymptote. Same thing is going to happen on the other side. Once the graph approaches the horizontal asymptote, it's going to slant horizontally, keep getting closer and closer and closer, and it's just going to go all the way to the left side. Now, the last 2 points. We have 1, 1. 1, 1 is here. Then the other point is 2, 0.25, which is here. So, when the graph gets close to this asymptote, as you can see, it is slanting horizontally, keep getting closer and closer, and it keeps going to the right. And on the other side, it keeps getting closer and closer to it on this side, and it's just going to slant vertically upward. So this is a graph of f of x that we saw in the picture in the previous slides. Now we're going to create the graph of g of x. Now for g of x, again, there are 2 transformations that we can apply. Number 1, we see that there is a -6 inside, so that creates a horizontal shift. That is the first transformation we need to apply. So what is that -6 inside of that, with the x is going to do, is going to shift it to the right 6 units, meaning that all of the x's will be added 6. Also this x. All of the x's will be added 6. And that is going to give us the following points and the following vertical asymptote. So that would be 4, 0.25. The next one is going to be 5, 1. The vertical asymptote is going to be x equals 6. So that's where my vertical asymptote is going to be. So let's go ahead and sketch that already. My vertical asymptote, it is going to be x equals to 6. Just going to extend it a little bit more right here. Now the last 2 points that we see there is the 7, 1, and the last one is going to be 8, 0.25. So let's go ahead and do the last transformation. Now the last transformation tells me now that we have a +5 on the side. What is that +5 going to do now? It's going to shift the graph up 5 units. So that means that this is going to be my final thing. We already did the x minus 6 squared. Now we're going to do the +5. And that is going to be added, as you remember, to the y values. So when it goes up or down, it is added to the y values. Now, those are not the only y values. There's also a horizontal asymptote, which that one is also going to be added 5. So my new horizontal asymptote is going to become y equals to 5. So this is where the new horizontal asymptote will be located. Now let's go ahead and connect those points so we can, get the points first so we can sketch it. So this first point right here, it's going to give us 4, 5.25. The next one is going to be 5, 6. Then the vertical asymptote stays the same. Then 7, 6, and the last one is going to be 8, and 5.25. So let's plot those points. So we have 4, 5.25. So let's put that here. 4, 5.25. It would be somewhere over here. Then 5, 6, which is here. So we can already connect that first side. The graph is going to slant vertically upward once it gets close to this asymptote, and it's going to slant horizontally to the left and keep getting closer and closer and closer to this asymptote, but it will never touch this asymptote. Okay. Now the last 2 points that we have in this graph is 7, 6. So 7, 6 is going to be right here, and the last one is 5.25, which is going to be, 8, 5.25, which is here. So once again, when the graph approaches this horizontal asymptote, it slants horizontally to the right, never getting closer to it, but it never touches this line. And when the graph approaches the vertical asymptote, it keeps getting closer and closer to it, but it never touches the asymptote. So this is my graph of g of x. Next, and basically the last thing that we're going to do is we are going to be graphing functions that cannot be graphed with transformations. So for functions that do not use transformations, we're going to use what is called the 7-step method described in the book to actually graph them. Okay? So this 7-step strategy, you can find it also in the textbook whenever you need to. And it tells me the following. Number one, you need to find out if the function has any symmetry. To find the symmetry of the function, what you have to do is that you need to substitute every x with a negative x. Now, if the function gives you the same thing back, remember, that means that the function is symmetrical with the y-axis. So f of negative x equals f of x means that it gives me back the original equation. Now, f of negative x equals negative f of x, that's origin symmetry. That means that the signs, all of the signs change. Now, but since this is a fraction, then when I say all of the signs change, that means the following. So think about a fraction. It is p of x over q of x, right? That's what the fraction is. In order for the fraction to, in order for the actual, that rational function to change the sign, basically we only need either for all the signs of the numerator to change or all of the signs on the denominator to change. Because if either the numerator or the denominator changes its signs, then that basically changes the sign of the fraction. If I have, for example, negative 2/3, negative 2 over 3, that's the same thing as negative 2/3. Or 2 over negative 3 is the same as negative 2/3. So whether the numerator or denominator changes the signs, then that's the same thing as changing the sign of the whole function. Okay? So that's when the origin symmetry is going to happen in the rational functions, when only one of them changes all of its signs. So now we're going number 2, we're going to find the y-intercept. To find it, we're going to replace every x with a 0, just like we did before. Now to find the x-intercept, there is a little strategy, a little shortcut for finding the x-intercepts. I'm going to show it to you the long way, but then I'm going to give you the shortcut. Now then we're going to find the vertical asymptotes. The vertical asymptotes, we find them by find those by setting the denominator equal to 0, finding the values of x that make the denominator 0. And remember, there might be holes. How do you know there's holes in the function? If there's any factor that can be reduced in the first place, that becomes a hole. That's called a removable discontinuity. Now, step number 5 is the horizontal asymptote. Using the 3 rules of the degrees, you need to determine what the horizontal asymptote is. If it's y equals 0, y equals to the division of the coefficients, or no horizontal asymptote. Then, step number 6, you're going to plot at least one point between and beyond each x-intercept and vertical asymptotes. So I'm going to go over that on the graph so you understand what that is saying. And then we're going to use all that information to sketch the graph. This is called the 7-step method described in the book. So let's go ahead and do a few questions here. We are going to begin with this one. Something simple, then we're going to increase the difficulty. Use the 7-step method described in the book to graph the following rational function. So, number 1, we need to find out if this function has either y-axis symmetry or origin symmetry or none. So, in order for us to determine the symmetry, we need to replace every x with a negative x. That's what we need to do here. So that would be a 3 times x, which is going to change to a negative x, over x, which is going to change to a negative x minus 4. So that 3 times negative x is negative 3x over negative x minus 4. Now, you see that the numerator changed the sign, but also the denominator partially changed the sign. So it did not stay the same as this function. So this function does not have y-axis symmetry because they are not the same. Also, not only the numerator changed the sign, but only partially the denominator changed the sign. So this one automatically has no symmetry, because for an origin symmetry, only either the numerator or the denominator must change all of its signs. And for y-axis symmetry, it must stay the same as the original function f of x. So right here we're going to say that there is no symmetry in this function. Let me write it on the side so I can have more space. So this function has no symmetry. Number 2. The second step in the process right here is that we need to find the y-intercept. To find the y-intercept, what we need to do is we need to replace every x with a 0. So it would be 3 times x, which is 0, divided by x, which is 0 minus 4. That's going to give us 0 divided by negative 4, which is still going to be 0. So the y-intercept is going to be the point 0, comma 0 in this graph. Now, before you find the x-intercepts or vertical asymptotes, step number 3 is finding the x-intercepts. The first thing you need to do here is you need to check if this function can be reduced. Okay? Now, check if you can factor. So to be able to reduce it, you need to check if you can factor. So 3x cannot be factored. X minus 4 cannot be factored. Okay, so this is already in lowest terms, so it cannot be reduced any longer. So one thing is this, that if you cannot reduce the function, that means that there is no holes automatically. Keep that in mind. Okay, there is no removable discontinuity, meaning that there is no holes. So now to find the x-intercepts, what you need to do is set the y, which is the f of x equals to 0, and you're going to solve for x. Now, in order for me to solve for x, whenever there is a fraction, then I need to multiply the denominator on both sides first. So what's going to happen if I multiply this denominator on both sides? Then it's going to simplify on this side, and when I multiply the x minus 4 times the 0, this is still going to give me a 0. So there is a little tip right here for you, that in order for you to find the x-intercepts, the x-intercepts of a rational function, you can find it by finding the zeros of the numerator. The numerator is 3x. So what does it mean by finding the zeros of the numerator? Set the numerator of this function equals to 0 and solve for x. So then I'm going to solve for x by dividing by 3, and that gives me x is equal to 0. So then my x-intercept is going to be x equals 0, so my y-intercept is 0, 0, my x-intercept is x equals 0, so it is the same point, right? So this point is the same for both. 0, 0, and x equals 0, of course. It's the same. Okay? So that's number 3. Now, for number 4, what you need to do next is you need to find the vertical asymptotes, if any. Now, something that we already said, that there is no holes, so you need to specify that. How do we know there's no holes? Because there's nothing that we couldn't simplify anything on this fraction, so there's nothing that there is no common factors from the numerator and denominator. So find the vertical asymptotes. Remember, the rule says that you're going to find the zeros of the denominator. That's all we need. So we're going to say x minus 4 equals to 0, so that gives you x equals to 4. That is the vertical asymptote of this function. So that means that the graph is going to slant vertically towards x equals 4, but it will never reach x equals 4. So let's go ahead and draw the vertical asymptote right here at x equals 4. Okay, that's where it's going to be. Now, the next one, number 5, it is going to be the horizontal asymptote. To find the horizontal asymptote, we need to look at the degrees. So if you look at this function, f of x equals to 3x over x minus 4, we can see that the degree of the numerator is 1 and the degree of the denominator is 1. Remember that this is n and this degree of the denominator is m. So you see that n is equal to m. What does that mean? How do we find the horizontal asymptote when the degrees are the same? You are going to divide the coefficients. Now the coefficients of this function are 3 and this one has a 1. So I'm going to divide those coefficients. 3 divided by 1 is going to give me the line y equals to 3. And that is my horizontal asymptote. So the graph is going to slant horizontally when it, once it gets close to y equals 3, right over here. This is what my horizontal asymptote is going to be. Okay? Now, to complete your graph, step number 6, we need to create a table. Now, for the table, I do things a little bit different. First, that's why, as you notice, I graph everything first. And then from there, I am going to decide what value. This is step 7 right here, the graph. From there, by looking at the graph, I will be able to determine what would be the values that I'm going to pick for the table. So, the values for the table will be the following. Now, you need to get at least, if you look at step 6, at least 1 point between and beyond each x-intercept and vertical asymptotes. What does that mean? This is an x-intercept and this is a vertical asymptote. So that tells you that you need to choose at least 1 point in between. That's first. Okay? So pick a point in between. So what can I pick in between? You can either choose either 1 or 2 or 3, whatever you want. So I'm just going to take it a little bit farther from this. So I'm just going to say the number 2. It doesn't matter which ones you pick, as long as you have at least 1 in between. I also need at least 1 point beyond the x-intercepts and the vertical asymptotes. What does it mean by beyond? Like on the left side of that x-intercept, that's beyond. So I need at least to choose 1 point, at least, on the left side of that x-intercept, whichever one you want. So I'm going to use -2 also, right there. Okay, and I also need at least 1 point beyond the vertical asymptote on this side. So whichever one you want. Now the word at least means that at least you need to have 1. The minimum is 1, but you can do more if you wish to do more points. Okay, so I'm just going to do what the instruction says. At least 1, so I'm going to use 1 for now. But remember, you can use more than that. On this side, I'm going to use, for example, the number either 5 or 6. I'm going to use 5. Okay, so this is the minimum number of points that I would need to complete this graph. So now, for +2, we're going to find the value of y by replacing these 2 into the x's. So that would be 3 times 2 divided by x, which is 2 minus 4. That is going to give us a 6 divided by -2, which is -3. So you get the point 2 comma -3 for that. So 2 comma -3. So here is it going to be. The next one, at -2, 3 times x, which is -2, divided by x, which is -2 minus 4. That's going to be -6 divided by -6, so that's going to give me a 1. So this point is -2 comma 1. So -2 comma 1, it is right here. And the last one, 3 times x, which is 5, divided by x, which is 5 minus 4. So it's going to be a 15 divided by 1, which is going to be 15. So this point is going to be 5 comma 15. So when x is 5, y is going to be all the way up right here. Let's pretend the 15 is right here. When x is 5, y is going to be 15, up all the way up here. Okay? So look at the left side of your graph. It is very similar, as you can see, to the graph of 1 over x. As we connect these 3 points right here, once the graph gets close to the vertical asymptote, it's going to keep slanting vertically downward. It's going to keep getting closer and closer, but it will never get to this value. Once the graph gets close to this horizontal asymptote, it's going to keep getting closer and closer, and it's going to slant horizontally to the left, but it will never touch the asymptote. That's what the left curve looks like. Now, let's do the right curve. Right here, this is where your point is. Now, you can do more points if you want to do it with more exactitude, but I think that that's more than enough. So we already know that the graph is going to be on this little section at the top right here. Okay? So once the graph gets close to this vertical asymptote, it's going to slant vertically up right here. And let me just move it up a little bit so you can see. So it's going to slant vertically upward right here, getting closer and closer to this asymptote right here, but it will never get to the asymptote. And once the graph gets close to this horizontal asymptote, it's going to slant horizontally to the right, getting closer and closer, but it will never get to that asymptote. This is approximately what the graph of 3x divided by x minus 4 will look like. And very similar to the graph of 1 over x, as you can see. Alright, now let's graph another transformation. We are going to, let's do this one. Use the 7-step method described in the book to sketch the graph of the following rational function. So, step number 1, we need to find out if this function has any type of symmetry. Now, to determine if this function has any type of symmetry, we need to do the f of negative x, meaning that I need to replace every x with a negative x right here. So it's going to give us 6 times x, which becomes a negative x squared, over x, which becomes a negative x squared, minus 4. Now if I square that negative x, that's going to become positive x squared times 6. It's just going to become a positive 6x squared. On the bottom, negative x squared, if I square it, that's going to become positive x squared minus 4. And then if you compare this to this, they are exactly the same equation. When they give you the same equation, that means that this function f of x is symmetrical with respect to the y-axis. So it has y-axis symmetry. That's what we can see on this function, that it has y-axis symmetry. Now, this is a step 7, and right here on the side we're going to do step number 6. So once we get to that, which is a table. Okay, but that until the end, almost. I'm going to leave that ready. So, the next item in the agenda, number 2, we need to find the y-intercept. To find the y-intercept of this function, again, we need to replace every x with a 0. So we're going to do f of 0 equals to 6 times 0 squared divided by 0 squared minus 4. That is going to give us a 0 divided by negative 4, which is going to be a 0. So the y-intercept is still going to be the point 0, comma 0 again. So this is my y-intercept right here, 0, comma 0. Number 3, we need to find the x-intercepts. Now, to find the x-intercepts, we first need to see if we can simplify this fraction. The numerator cannot be factored, but the denominator, it can be factored. X squared minus 4, if you remember, this is a squared, which is x squared, minus b squared, which is 2 squared. And that factors into a plus b, which is x plus 2, times a minus b, which is x minus 2. Now, let me ask you this. Can I simplify any of these factors with the numerator? No, because the numerator does not have any x plus 2 or any x minus 2. So this one, it's already simplified. Okay, so what does it mean by that? That there is no what on the function. Since we cannot reduce or remove any of these factors, then there is no removable discontinuity, meaning there is no holes in the function. So, to find the x-intercepts, remember what's going to happen. So all I need to do is find the zeros of the numerator. That was a shortcut. So all I need to do is set the numerator equals to 0 and solve for x. So I'm going to divide by 6 on both sides, so I get x squared equals to 0. And to get rid of the square, I need to take the square root on both sides, and you put a plus or a minus, right? But the square root of 0 is 0, so do I really need the plus or the minus? No. So it is just x equals 0. And we already have that plotted, so it is the same as this one. Okay? So far, so good. Now, number 4, we're going to find the vertical asymptotes. To find the vertical asymptotes of a rational function, what we need to do is we need to find the values of x that make the denominator 0. So right away you can say that there is no wholes, because there was no factor that could be reduced. Okay? Now for the vertical asymptotes, we need to set the denominator equals to 0, which is x plus 2 times x minus 2, set it equal to 0, and solve for x. So if I set this equal to 0, and if I set this equal to 0, then my vertical asymptotes will be x equals to -2 and x equals to +2. Those are my vertical asymptotes. So what does that mean? That when the graph approaches x equals to 2 and x equals to -2, it's going to slant vertically upward or downward depending on where the graph is going. If it's going up, then it slants vertically upward. If it's going down, then it slants vertically downward. Okay, that's what it does when it gets close to the asymptotes. And last but not least, now we're going to find the horizontal asymptote before we can create the table. Now, to find the horizontal asymptote, we're going to do the same thing as usual, which is we're going to look at the degrees. So I'm going to look at the degrees. So let's look at the original. The original says f of x equals 6x squared, because on the factor one, I cannot see the degree. So right here, what we can see is that the numerator and denominator, which is my n and my m, both of them, they have the same degree. So if we have the same degrees on the numerator and denominator, then how do we find the horizontal asymptote? By dividing the leading coefficients, which is the 6, and in front of the x squared there is a 1. So it would be 6 divided by 1 gives me y equals to 6. And that would be the equation of the horizontal asymptote. That means that when the graph approaches y equals to 6 right here, from the left or from the right, it's going to slant horizontally to the left and horizontally to the right. It's not going to get to that value. Last but not least, now we're going to create the table before we can make the sketch. Let's make the table. Now for the table, remember that you need to choose at least one point between the x-intercepts and vertical asymptote. So I need at least one point between this x-intercept and this asymptote, and one point between this x-intercept and this asymptote. So we have only two values that we can select, -1 and +1. So let's use those, -1 and +1. Now we also need to select at least one point beyond and beyond. Beyond means on the left side of this asymptote, I need to have at least one point, and on the right side of this asymptote, I need to have at least one point. So let's say we pick just -4 and +4. Okay, so then we're going to substitute them to find the values of y. Remember that we only need at least one, but if you want to, can you do more? The answer is yes, because at least means that it has to be at the minimum, at the least, at the minimum it has to be 1, but it could be more. So 6 times x, which is -1 squared, divided by x, which is -1 squared, minus 4. So we're going to get 6 times 1 divided by 1 minus 4. That's going to be 6 divided by -3, which is -2. So we get the point -1 comma -2. But wait a minute. Since this function we said on the number 1 that it has y-axis symmetry, that means that whatever we get on the -1 should be the exact same value as +1. These two should be exactly the same thing because the function is symmetrical with the y-axis. So that we don't need to do it. It has to be -2 as well. So we get also 1 comma -2. The next one, let's do -4. 6 times -4 squared divided by x, which is -4 squared minus 4. So -4 squared is 16. So it's 6 times 16 divided by 4 squared, which is 16 minus 4. So we're going to get 96 divided by 12. And that is going to be 8. So when x is -4, y is going to be 8. Also, that means that when x is +4, it should also be the same thing. That is also should be an 8. We don't need to do it. So that would be a +4 comma 8. So let's graph those points so we can finalize the graph. -2, -1, comma -2, that's this point here. +1, comma -2, that's this point here. So you see that the graph on this side, it kind of looks like a parabola going downward. So when the graph approaches this asymptote, it's going to keep getting closer and closer and closer, and it's going to slant vertically downward, and it's going to keep getting closer and closer and closer, slanting vertically downward as well to this side. So that's what the middle looks like. Now the other points, -4,8, -4,8 is up here. So that means that the curve from this section is going to be on this little piece on the top. Okay. So when the graph gets close to this asymptote, it's going to slant vertically upward right here, and when it gets close to this asymptote, it's going to slant horizontally to the left. Now the last point is 4,8. 4,8 is right here. So as the graph gets close to this asymptote, it's going to slant vertically upward right here, and when it gets close to this asymptote, it slants horizontally to the right. And this is what the graph of this function will look like. And you see that it is symmetrical with respect to the y-axis. This looks exactly the same as this on the other side. This little piece, half of the parabola, looks exactly the same thing as this other side of the parabola. This asymptote, we can also see it reflected on this other side. That concludes this question. Now, we are going to graph one more, and that is going to be, yes, this one. Use the 7-step method described in the book to graph the following rational function. Okay. So, number one, we need to find out if this function has any symmetry. To determine the symmetry, we have to replace f of -x, meaning that every x is going to be substituted with a -x. -x squared plus -x minus 6. So if I do that, then we're going to end up with -x plus 2 over x squared minus x minus 6. Did the equation stay the same? It didn't. So there is no y-axis symmetry. We can discard that choice. Did the numerator change both of its signs? Nope. Did the denominator change all of its signs? No. So that means there is no origin symmetry either. So this problem has no symmetry. That's what we're going to say. There is no symmetry. Okay. So, number 2. Now we're going to find the y-intercept. To find the y-intercept, we have to set every x equals to 0. So we're going to say f of 0 equals to 0 plus 2 divided by 0 squared plus 0 minus 6. That is going to give you 2 divided by -6. That's what that is going to be. 2 divided by -6, which is -1/3. So my y-intercept is 0, comma, -1/3, or -0.33333. So that means that it's going to cross the y-axis right over here, somewhere on this little area, on this little region. Okay. Now, number 3. Before we can answer question number 3, remember what we have to do. That one, we need to find the x-intercepts. For this step 3, what we need to do is we need to check if this function can be reduced. So we need to factor it first. So the numerator cannot be factored, but the denominator can. So we need to, for the denominator, we need to multiply a times c because it's a trinomial. So we have 1 times 6, it's going to be a 6. We need to find two numbers that multiply to 6. And when we subtract them, they give me a 1. So that would be a 3 times 2, positive 3 and negative 2. Let me ask you the following. Can I reduce the x plus 2 with the x minus 2? The answer is no, because they are not like factors. X plus 2 and x plus 2 will be, or x minus 2 and x minus 2 will be. But x plus 2 and x minus 2 are different factors. So it cannot be reduced. So that automatically tells us one thing, that there is no holes, because there is no removable factors or removable discontinuity. Okay. So how do we find the x-intercepts? We just have to find the zeros of the numerator. So we set the numerator equals to 0 and solve for x. So that gives us x equals to -2. This is where the graph is going to cross the x-axis. Let's plot that on the graph. X equals to 2. Right here. Oh, not 2. -2. Right? X equals -2. Right here. Now, how do we find the number 4, which is the vertical asymptotes? By finding the zeros of the denominator, right? So we find them by finding the zeros of the denominator. So we're going to say x plus 3 times x minus 2 equals to 0. So if I solve for x, you get x plus 3 equals to 0, and right here x minus 2 equals to 0. So x equals to -3 and x equals to +2. Those are the vertical asymptotes. And automatically we already said that there are no holes, because there is no factor that can be removed. So those are my vertical asymptotes, meaning that the graph is going to slant vertically once it gets close to these lines, to these numbers. So we're going to have a vertical asymptote at -3 right here. So the graph is going to slant vertically upward or downward once it gets close to that line. So let me make it more exact. And it's going to slant vertically upward or downward once it gets close to x equals to 2 right here. So now let's go ahead and sketch, not the table, not yet. We need to find the horizontal asymptote. That would be step number 5. For the horizontal asymptote, we need to look at the degrees. So my function, I'm going to use the original function, which is x minus 2 over x squared plus x minus 6. What do we notice about the degrees right here? The degree of the numerator is a 1, that is my n. The degree of the denominator is a 2, so that is an m. So right here we can see that n is less than m. So if the numerator is less than the denominator, then this function is going to have a horizontal asymptote at the line y equals to 0 by definition. So then it's going to slant horizontally once it gets close to this line right here, y equals to 0. Okay. Next. Okay. And it is okay, as you can see, that the graph could cross the horizontal asymptote. It is okay. That happens only, of course, if there's an x-intercept. But the graph will never cross the vertical asymptote. That is for sure. That's a fact. But it could sometimes cross the horizontal asymptote. And right here it will, because as you notice, we have an x-intercept on this graph at that same location. Right? So now let's go ahead and create the table. This is my step 7, but my step 6, we need a table for this. Oops. So this function is f of x equals to x plus 2 over x squared plus x minus 6. So then we need to remember what the definition states, that you need to have at least one point between and beyond each x-intercept and vertical asymptote. So right here between this x-intercept and vertical asymptote, we don't have that much of a choice. So I'm going to use -2.5. I'm going to use that. Right here between this x-intercept and this vertical asymptote, we don't need anything because you see that we already have a point there. Right. Now, right here beyond. Now let's look at beyond. Beyond the vertical asymptotes, we need at least 1 point on this side and at least 1 point on this side. At least 1 means that you can get more than 1. It's up to you. So let's say we get 3 and -4. So I'm going to use the -4 and the +3. Those are the ones I'm going to use. -4 and +3. Now we're going to find the y values by substituting those x values into the function. So we're going to have x, which is negative 2.5 right here, plus 2, divided by x, which is negative 2.5 squared, plus negative 2.5, which is x, minus 6. Let's do that here. Negative 2.5 plus 2 is negative 0.5, divided by negative 2.5 times negative 2.5 is going to be 6.25. So we put negative 2.5 and we square it. That's going to give you 6.25. So that's going to be 6.25 minus 2.5 minus 6. So let's see what that gives us. 6.25 minus 2.5 minus 6. That is negative 2.25. So then that's going to give us the point, I'm going to put it right now. That's going to give us the point negative 2.5, comma, negative 2.25 for that one. Now, the next one, x, which is negative 4 plus 2 over x squared, which is negative 4 squared, plus x, which is negative 4 minus 6. So negative 4 plus 2 is negative 2 over 4 squared is 16 minus 4 minus 6. 16 minus 4 is going to be a 12. 12 minus 6 is going to be a 6. So that's negative 2 over 6. And negative 2 over 6 is negative 1/3. We can put it as an estimate, negative 1/3. So this negative 4 comma negative 1/3, but that will be negative 0.3. Okay. So that's basically what it would be. This is estimated to negative 0.3. Right. Now the next one. Negative, x, which is going to be a 3 plus 2 over x, which is 3 squared, plus x, which is 3 minus 6. 3 plus 2 is going to be a 5 over 3 squared is going to be a 9 plus 3 minus 6. That's going to give us a 5 over 9 plus 6, which is 12. 12 minus 6 is going to be a 6. So that gives us a 5 over 6. So it's going to be 3 comma 5 over 6. This one, as an estimate, we can divide it out to find its estimate. That will be like about 5 over 6. I'm sorry, 0.83. So it will be about 0.8 approximately. So let's go ahead and graph those points. So when x is negative 2.5, y is going to be, let me see, negative, 1 second. Oh, there was one little thing that I forgot here. This was supposed to be negative 0.5 divided by negative 2.25. The negative 2.25 is from the denominator. So let's go ahead and divide that. So we have negative 0.5 divided by negative 2.25, and that is 0.2. So that should be approximately 0.2. So let's change that up here. So that should be a 0.2. So then we're going to get negative 2.5 and 0.2. So negative 2.5 and 0.2, the point is going to be somewhere in here, as you can see. So what do you see? If you connect these 3 points in the middle, okay, that's what you see. And remember what happens. When the graph gets close to this vertical asymptote, it is going to start slanting vertically downward right next to the asymptote, getting closer and closer to it. And when the graph gets close to this other asymptote, it is going to slant vertically, but in this case it is going upward towards the asymptote. That's what the graph shows us in the middle with these 3 points right here. It is going down, right? That's what we see. So the next one, negative 4 comma negative 0.3. Negative 4, negative 0.3, it is right here on the bottom. So we can already sketch this side. So you see that the points on this curve is going to be on the bottom side. So when the graph gets close to this vertical asymptote, it's going to slant vertically downward right here. And when the graph gets close to the horizontal asymptote, it's going to slant horizontally to the left. Look at the last point, 3 comma 0.8. 3 comma 0.8, it is somewhere over here. So when the graph gets close to the vertical asymptote here, it's going to slant vertically upward right next to the asymptote. and when the graph gets close to the horizontal asymptote, it's going to slant horizontally to the right. And this is what the graph of this function is going to look like, based on the points that we selected. Now, we're going to do one more definition, and that will be the end of the section. The last definition is going to be the slant asymptotes. Now, what does it mean by a slant asymptote? I gave you the definition of what it is in a graph. It is a diagonal asymptote. That's basically what the slant asymptote is. Okay. Now, a slant asymptote, which is a diagonal asymptote, replaces the horizontal asymptote basically. So whenever there is no horizontal asymptote on a function, it could be that there's a slant, but not necessarily, but it could be. Now, how do we determine that there's a slant asymptote? This is the definition. The slant asymptote happens if the degree of the numerator is, and this is the main idea, the degree of the numerator is 1 more than the degree of the denominator. So, for example, if the degree of the numerator is x cubed, the denominator is x squared. Or the degree of the numerator is x squared, the degree of the denominator is x. So when the difference between the numerator and denominator is that the numerator is 1 bigger, okay, that's when we're going to have this kind of asymptote right here. How do we find this asymptote? We find the slant asymptote by using long division or synthetic division, dividing the polynomial. By dividing the two polynomials of this function. Okay, if we divide them, we're going to get that slant asymptote. So, my last question for this section is going to be this one. We're going to use the 7-step method described in the book to sketch the graph of this rational function. Number 1. First thing is we need to find out if there is any type of symmetry. To determine if there's any type of symmetry, we need to replace every x with a negative x. So that's what we need to do right here. Replace every x with a negative x. So then this is going to give us right here over x, which is negative x minus 6. So if I simplify it, that's going to be x squared plus x minus 20. And that is going to be over negative x minus 6. If we compare this to the original function, they are not the same, meaning that this function is not symmetrical with respect to the y-axis. And also we can see that not the numerator changed all of the signs, not the denominator changed all of the signs. So automatically that means that there is no origin symmetry. So this function has no symmetry at all. Number 2. Second thing that we need to find is we need to find the y-intercept. How do we find the y-intercept? By substituting every x with a 0. This is going to be 0 squared minus 0 minus 20. That is going to be divided by 0 minus 6. So that's going to give me negative 20 divided by negative 6. And we can reduce this to 10/3. So my y-intercept is going to be the point, hold on, because it's getting stuck here. It's going to be the point 0, 10/3. That is my y-intercept. So what does that mean? That is going to cross the y-axis at 10/3, which is 3.3. So this is where my y-intercept is going to be, approximately. Number 3. Now we're going to find the x-intercepts. Now to find the x-intercepts of a function, we need to set, first of all, we need to check if we can simplify it, right? So that's the rule number 1 here. And the numerator of this function can be factored. So we need to see if there's any factor that can be divided out, because there might be holes, remember. That's one thing that we need to be careful. So for this numerator, we can multiply a times c, which is 1 times 20, which is going to give me a 20. So we need to find out two numbers that multiply to 20, and when I subtract them, they give me a negative 1. And that's going to be a 5 and a 4. Of course, negative 5 and positive 4. So it would be x minus 5 and x plus 4. What do we notice right here? Can I divide out any of these factors with the x minus 6? The answer is no. So that automatically tells you that there are no holes in this function either. Okay? So to find the x-intercepts, all we need to do is find the zeros of the numerator. So that's all we need. Find the zeros of the numerator. So if I set this equal to 0, x minus 5 equals to 0, and x plus 4 equals to 0, that is going to give us x equals 5, and right here x equals negative 4. So these are the zeros of the x-intercepts, those two. Okay, so let's put the x-intercepts here, 5, which is right here, and negative 4, which is right here. Those are the x-intercepts. Now, step number 4, we need to find the vertical asymptotes. Before we find the vertical asymptotes, one thing that we can say is that there are no holes, because no factor was able to reduce, so there are no holes in this function. Now, to find the vertical asymptotes, we have to find the zeros of the denominator. So we set the denominator equal to 0, and we solve for x, which is x equals to positive 6. This is the vertical asymptote. So that means that the graph is going to slant vertically once it reaches x equals to 6. So this is how it's going to look like right here. Once it reaches this value, it's going to slant vertically downward or vertically upward. And this graph was supposed to go all the way to the 20s. I just picked a wrong graph, so I'm going to extend it a little bit higher right here. Now we're going to do the horizontal asymptote. That is going to be my last one here, number 5, before we get to the table. For the horizontal asymptote, we need to look at the degrees. So if we look at the degrees of this function right here, so let's look at the original. F of x equals x squared minus x minus 6 divided by x minus 6. I mean x minus 20 divided by x minus 6. So what I want you to look at is that the degree of the numerator right here is 2, that's n, and the degree of the denominator is 1, that's m. So right here, n is bigger than m. When that happens, remember the definition says that there is no horizontal asymptote. And this is when we have the possibility that the horizontal asymptote is going to be replaced by a slant asymptote. When does the slant asymptote happen according to the definition? When the degree of the numerator, it is exactly 1 more than the degree of the denominator. So 2 is bigger than 1 by 1 more. So that means that there's a slant asymptote. Now, in order for us to find the slant asymptote, what we need to do is we need to divide this rational function. So we're going to use synthetic division or long division. What I do recommend, of course, as usual, if you can use synthetic division, use synthetic division. You see that the coefficients of that numerator, it is 1, negative 1, and negative 20. And now for the denominator, remember that I need to set the x minus 6, I need to set it equal to 0 and solve for x. That gives me x equals to 6. I'm going to put the 6 on the outside. Now, if you prefer to use long division, that is completely okay. So, bring the 1 down. Then we're going to multiply. 6 times 1, that's going to give me a 6. Then negative 1 plus 6, that's going to be a 5. 5 times 6 is going to be a 30. Negative 20 plus 30 is going to be a 10. And the 10 represents the remainder. So, for your slant asymptote, you're going to write it like this, y equals to, and you're going to put whatever's left without including the remainder. The remainder, we're not going to use it. So remember that when I divide with synthetic division, this degree decreases 1 time, so that the degree of this one is going to be x to the first power. So it's going to be 1x plus 5. You don't have to put the 1. You can just say y equals x plus 5 would be your slant asymptote. So, let's go ahead and graph that slant. Y equals to 1x plus 5. Remember, this is a line that has a y-intercept of 5 and it has a slope of 1 over 1, meaning that it goes up 1 to the right 1, up 1 to the right 1, up 1 to the right 1, and so on and so on and so on. So that's what my slant asymptote right here will look like. And it just continues. It's just going to extend over this side, and it's going to extend over to this side. Finally, to complete this graph right here, what we are going to do, we're going to choose some points. Okay, we're going to choose some points to create the table. Okay, so that we need to create a table for this. And on that table, you need to have at least one point between and beyond the vertical asymptotes and x-intercepts. So this is step 7. So we're going to go through step 6. So let's create a little table. Let's see what values are we actually missing. So the function is f of x equals to x squared minus x minus 20 divided by x minus 6. Now, between and beyond the x-intercepts and vertical asymptotes. So I need at least one point in between these x-intercepts. So between the x-intercepts, you see that we already have that one. So if you want, you can do more, but it is not actually needed because I already have at least one point between them. Now, there's a between this x-intercept and this vertical asymptote. So let's pick 5. So I'm going to pick right here between these two, 5.5. So 5.5 is going to be my value, not negative. Positive 5.5. And beyond this vertical asymptote, I need at least one point, so you can pick whichever one. So what if we pick 8, or yeah, let's pick the number 8 or the number 9, whichever one. So I'm going to pick 9 this time, right here. Okay, I'm just going to pick one. So let's substitute them to find the values of y. So we already picked one number in this side, and we already picked one number between these two. And we already had the number between those two. So that one was that one. So we just needed these two right here. So 5.5. So we're going to have 5.5 squared minus 5.5, which is x minus 20. That is going to be divided by 5.5 minus 6. I'm going to find that numerator in the calculator. So 5.5 squared minus 5.5 minus 20, so the numerator is 4.75. Now 5.5 minus 6 is negative 0.5. So if I divide them, 4.75 divided by negative 0.5, that is going to give us negative 9.5. So you see that the first point is 5.5 and negative 9.5. So right here at 5.5, the value of y is going to be all the way at the bottom down here at negative 9.5, which is somewhere right here in the middle. Now on the other one, if I put a 9, it is 9 squared minus 9 minus 20, everything over 9 minus 6. That's going to be 81 minus 9 minus 20 over 3. 81 minus 9, it's going to be 73. 73 minus 20 is 53. Then 53 divided by 3. 53 divided by 3, that's going to be a 17.6. So this is approximately 17.6 or 17.7. So that means that when x is 9, y is equal to 17.7 approximately. So when x is equal to 9, y is equal to, let's assume that the 17.7 it's going to be right here. So let's say this is 17. Okay, so 11, 12, 13, 14, 15, 16, 17, and then 18. Okay, so 9 and 17.7 is basically going to be somewhere over here. So what does it mean? Well, let's put this together. So the graph is going to contain these 3 points. So you need to connect this point, and then it's going to turn over to this point, and then it's going to go over to that point. And remember that the graph is going to keep getting closer and closer to the vertical asymptote, likewise is going to keep getting closer and closer to this slant asymptote. What about from the top? When the graph is going to keep getting closer and closer to this slant asymptote here, and then it's going to keep getting closer and closer to that vertical asymptote. These are the two pieces of the graph, the left side and the right side. Okay. And this concludes section 3.5, which is rational functions and their graphs.